here. Yeah, I don't know, but it's here, so so I guess we'll work this one. As I mentioned last week, you know, exponential functions and logarithmic functions go hand in hand. And basically, if you're solving, in this case, you're solving an exponential equation, meaning that the variable is up in the exponent. And of course, to solve the equation, you know, means eventually it'll say x equals something. So you're going to need logarithms to get the variable out of the exponent, basically. All right, that's pretty much what is going on. So there are a couple ways to do this, but what you definitely want to do first is get rid of that 1/3. So simplest thing to do would be just to multiply both sides by 3 in order to basically get rid of the fraction. And what we're really trying to do here is get the exponential part by itself. All right. That is the e to the negative 3x. That's the exponential part. So from here, there are also there are two ways that you can go. I would say probably what makes most sense is to take the natural log of both sides. That is a legitimate thing to do in the world of equation solving. You know, sort of like you can take the square root of both sides of an equation, or you can square both sides of an equation. It's also legitimate to take the logarithm of both sides. And the reason that we're using the natural log is that the equation involves the number e. All right, so take the natural log of both sides. The reason this is helpful is, remember that one of the properties, I don't know which number it is, but one of the properties, I guess we can find it. It is property 3 up here, that when you're taking the logarithm of a to the k, and the logarithm has the base a, so log to the base a of a to the k is just k. Like, this is kind of a canceling situation. It's really an inverse situation. So log with the base e of e to the negative 3x is just 3x. And that's property 3 from above. Oh, that's nice. Okay, so that just becomes negative 3x. Natural log of 2.7 is just a number that we can put into our calculator. So what I would do is just go ahead and divide both sides by negative 3. So x is the natural log of 2.7 divided by negative 3. And just be sure when you compute that, that you put the 2.7 in parentheses, or that you actually close the parentheses after the 2.7. So when I compute this, I get negative 0.331, and that's it. Okay, so basically solve for x. All right, and again, that's still algebra. I guess just a use of logarithms is to solve an exponential equation. All right. Okay, so now finally we're ready to do some derivatives. And like I said, we only work on natural log functions, the ln. We're only doing derivatives of natural log functions. So sort of like with our exponential functions, there was the simple case that the derivative e to the x is e to the x. This is also the simple case for the natural log. The derivative of the natural log of x is 1 divided by x. Okay, the derivative of natural log of x is 1 divided by x. Wish I could make that thing go away. All right. What? Hang on a second. Okay. All right, so like I said, this is where x is the single variable I guess I should add in there with the coefficient of 1. So just x, nothing else. Or, you know, whatever the variable is. Okay, so that's our simple case. The first example says find the derivative of 4 times ln of x. So for y prime, we hang on to the 4. So again, the rules from finding derivatives in general come into play here. 4 is the coefficient of the function. So we just keep the 4 and multiply by the derivative of the function. So keep the 4. The derivative of ln of x is 1 over x. That's pretty much it. You can rewrite that as 4 over x. It's probably how you would see that written. All right. Okay. Problem 10. So I'm going to put parentheses around those to show it as a product of two functions. This is a product of two functions. So to begin the derivative, we'll use the product rule. Okay. Product rule. First function times the derivative of the second function. And then we swap the two around, the derivative of the first function times the second function. So I'll write that again. The derivative of the product u times v, u times the derivative of v plus v times the derivative of u. All right. All right, so we've got x squared. This is our new formula. Derivative of ln of x is 1 divided by x. On the other side, the derivative of x squared is 2x. And that's pretty much it. You can do a little bit of simplifying. You can think of x squared over 1. So that's really x squared divided by x. And then you can divide x squared divided by x is simply x. And then you have a simpler version. All right. So that's it so far. And if you have a question. Okay, now we have the quotient rule. Oh, we're gonna need some more room here. So remember the quotient rule. For the derivative of a quotient u divided by v, or numerator divided by denominator. So it's the denominator times the derivative of the numerator minus, and then you swap those around. So denominator times derivative of numerator minus numerator times derivative of denominator, all over the denominator squared. That's our quotient rule. And so, all right, I'm just going to just leave that there, and maybe it'll leave me alone. All right, so actually, I'll start with y prime. Put that over here, y prime. So the denominator x cubed times the derivative of the numerator, ln of x, minus the derivative of the denominator times the numerator. And that's all over the denominator squared. Remember, after we set up the quotient rule, then we take our two derivatives that are inside the quotient rule formula. Here's my new formula. Derivative of ln of x is 1 divided by x. On the other side of the subtraction, the derivative of x cubed is 3x squared. And we'll go ahead and use it. Remember, that's a rule of exponents, that if you have a number with a power and that is raised to another power, then you keep the base and multiply the powers. So that's how the 6. All right. So thinking of x cubed, thinking of that as over 1, x cubed over 1 times x, and you could probably do this in your head, but I'll go ahead and write it. That's going to be x cubed divided by x, which I'll simplify. X cubed divided by x is x squared. Whoops, that should be 6. All right. And, you know, that answer is okay, but you can do some simplifying. You know, and that's, you know, as I've been saying now for 10 weeks, the algebra inside of the calculus is, sometimes it's more difficult, but it's certainly, there's certainly algebra involved in calculus. You can simplify this by factoring out the common factor between the terms in the numerator. There's an x squared. And then there is also a factor of x squared in the denominator. So I'm factoring out an x squared. Now, so when I took out the x squared from the first term of the numerator, I'm left with a 1, and then 3 minus 3 ln of x. And for the denominator, I'm thinking about, I want to factor out an x squared. So now you've got to think about another rule of exponents in reverse, basically, that a to the m times a to the n is a to the m plus n. So I wanted to think of x to the 6. I wanted to break that down as x squared times x to the 4th, so that now I can divide out the x squared, okay? So finally, that's 1 minus 3 times ln of x, all divided by x to the 4th for my simplified answer, all right? The main reason that you need these things simplified would be if you're using the derivative to find out maybe critical values, if you want to see where your function is increasing or decreasing, relative max and min. That's the purpose of simplifying. Excuse me. Okay. All right. Now we have the non-simple case. And that is where you're finding the derivative of the natural log of some function that's something other than just a single variable x. Although this rule works for the single variable x too. All right, and notice that it starts off the same. This simple rule, or the simple case, is that the derivative of natural log of x is 1 divided by x. It's actually a type of chain rule. I'm trying to think of a way to describe it. I'm just going to call it that because that's really what it is. It's the chain rule for the exponential function, or it's the non-simple case. I don't know, maybe that you like that better. So let me just rewrite it this way. Instead of x, I'm using u. So this is where u is a function of x, which is basically anything besides x. 5x, x squared, x minus 7, anything other than just plain old x. All right, so again, notice it starts off the same way. And I guess if you wanted to express this in words, this is what you're doing. It's 1 divided by the function times the derivative of the function. And it's kind of a strange rule, but that's the rule, okay? So it's 1 divided by the function times the derivative of the function. All right, so for number 12, you got the natural log of 5x. So 5x is the function. So for my derivative, it's 1 divided by the function times the derivative of the function. And then that's pretty straightforward. The derivative of 5x is 5. And then you can always think of 5 over 1. So the 5's cancel. And it turns out the derivative of this is just simply 1 over x. Okay? All right. For number 13, that x cubed is the function. So for the derivative, f prime of x, it's 1 divided by the function times the derivative of the function. Okay? So 1 divided by x cubed, the derivative of x cubed is 3x squared. Then you can think of that over 1. So this becomes 3x squared divided by x cubed. And then you can simplify the x squared divided by x cubed would leave a single x in the denominator. So 2x's in the top of the fraction, 3x's in the bottom of the fraction. 2 pairs of x's cancel out and leaves 1 in the denominator. All right. Okay. Now, for number 14, all right, again, the function is what's in parentheses. So, for the derivative, 1 divided by the function times the derivative of the function. And then keep going. So I've got 8x cubed minus 2x. For 8x cubed, the derivative is 3 times 8 would be 24. Subtract 1 from the power, leaves x squared. And then for minus 2x, the derivative is minus 2. All right, let's see. Again, I can think of that over 1 so that I can multiply the fractions together, but also not a lot of simplifying that I can do. But I could factor out a 2 from everything. All right, so 2 factored out of 24 would be 12x squared. 2 factored out of 2 is 1. And the denominator, 2 factored out of 8x cubed is 4x cubed. And then 2 factored out of 2x leaves x. So that, like I said, now I can cancel the 2's. And there's my final, that's my final answer. There's nothing else I can do to that. Some people may be tempted to do something else to that, but there's nothing else you can do to that from a simplifying standpoint. All right. So, all right, so that's that one. Now, all right, number 15. Okay, so that might look a little intimidating. First thing I'm going to do is write it this way so you can see that this computer just has got a mind of its own. Do it again. This is a product. I wrote the way I wrote it. With e to the x in the parentheses. So it's a product of two functions. Therefore, when I'm getting its derivative, I'm going to use the product rule. Okay, so product rule, I've done that a couple times now in this section for the derivative. Okay, so keep the first function times, I'm going to use this notation, just kind of switch it up a little bit. First derivative, derivative of the first function times the derivative of the second function plus I think I have this under control and then I don't. All right, plus the derivative of the first function times the second. So that's just your good old product rule. We set it up in the first step and then compute the derivatives in the second step. So we'll keep going, keeping that e to the x. All right, here's the new rule for this section. My function is that 2x plus 3. So for the derivative of the ln of a function, the rule is 1 over the function, 2x plus 3, times the derivative of the function. Okay. All right. The derivative of e to the x, that's from the previous section, and it's also the simple case. It's a simple case. The derivative of e to the x is e to the x. I don't know, you might want to keep in parentheses. And that's times the ln function that we didn't bother. All right, and so this is the simple e to the x rule. Derivative of e to the x is e to the x. All right, I need to do this little derivative right here. I've got e to the x, 1 over 2x plus 3, and then the derivative of 2x plus 3 is 2. Then it gets better. Try going into tablet mode. I can't figure out what makes this thing tick. Plus the other stuff, I'm just basically copying it. All right. Now, that's pretty much it from a derivative standpoint. About the only other thing you do here, where I just wrote those ones, if you think of those over 1, then you can actually multiply all those, the three fractions, you can multiply those together. The rule is multiply all the numerators, so that would be 2e to the x. And then 2x plus 3 is the denominator. And that's about it. Okay. Kind of a complicated looking answer, but that is the answer. All right. Okay. Any questions on that one or anything so far? Let's see, that's about 16. Oh yeah. Okay. So yeah, we probably needed the day to finish up this section anyway. I thought. I'm very confused now. I don't know what I'm. Okay. I'm gonna get some more space in there. Okay. For 16, it says hint, rewrite using properties of logarithms before, here we go again, taking the derivative. And you need to just trust me on that, because if you didn't do that, you would have a mess. And sometimes I show you what it would look like if you didn't use my hint. But just imagine the rule for that. So okay. I just don't know how frustrating it is to have this thing pop up all the time. Okay, there it is, gonna do it again. That's nice. Okay, so what I'm putting in parentheses, that's the function, right? What we've done before. And what's the rule for getting this derivative? 1 divided by the function times the derivative of the function. Yuck, right? That 1 divided by a fraction times the derivative of a fraction. I mean, I don't know if you can imagine that in your head, but that's going to be messy. You got 1 divided by a fraction, and then for the derivative of the fraction, you'd have to use the quotient rule. So luckily, you know, we have these properties of logarithms that will help us simplify before we get the derivative. All right. So first thing I'm going to use is the quotient property. I'll probably get a kick out of me getting so frustrated with this. I don't know. It's just, ugh, can't figure it out. Quotient property of logarithms. So this is an algebra thing. Says, okay, the logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. All right, that's the quotient property. And then we can even go further. The power property of logarithms lets you do something different with x to the 4th. Okay. Man. I really wish I could just move this. Make it smaller. Okay, so the power property lets me take that power of 4 and basically move it in front and multiply it by the log of x. Okay. All right, so that's it. I've used all the properties I can. The only other property there is the product property, and that's for the logarithm of a product, but I don't have any products, so that's as far as I can go. All right, now I can use my derivative rules. For the derivative, hang on to the 4, and for ln of x, that's the simple case. The derivative of ln of x is 1 divided by x. Now, 3x plus 1, that's the function that's in the parentheses. For the derivative, remember, 1 divided by the function times the derivative of the function. And then one more little derivative right here, the derivative of 3x. All right, so I've got 4 times 1 over x, 1 over 3x plus 1. The derivative of 3x plus 1 is 3. And then the only other thing I'm going to do is put those constants over 1 and simplify the fraction. That's 4 over x minus 3 over 3x plus 1. All right. And that's my answer. All right. Okay, here's another one that's similar. Again, it says hint rewrite using properties of logarithms. And again, what I mean there is before taking the derivative, because you just, you definitely want to do that. So inside, let me rewrite it. Inside the parentheses, make them brackets, I have x to the 5th times the square root of 3x plus 2. So what I have right here is a product. And I'm going to use the product property of logarithms to separate those. Okay, brain work. Product. I'm using the product property of logarithms to separate the stuff that's in those parentheses. Okay, this is the product property. It says, okay, that's the ln of x to the 5th plus the ln of the square root of 3x plus 2. Well, and I always say, you know, logarithms and radicals don't go together very well. Logarithms and exponents do go together well. And so instead of using the square root of 3x plus 2, you want to rewrite that as 3x plus 2 to the 1/2. All right. Why? Because then I can use another property of logarithms. So I rewrote that as the 1/2 power. Why? Like I said, because now I can use the power property of logarithms. Those powers by the product, I'm sorry, the power property. That becomes 5 times ln of x plus 1/2 times ln of 3x plus 2. And just way easier to get the derivative at this point than it would have been in the beginning. All right, so I've now used all the properties of logarithms I can. Now ready for my derivative rules. Hang on to the 5. ln of x, that's the simple case. So the derivative of ln of x is 1 over x. Keep the 1/2. All right, and 3x plus 2 is the function. The natural log of a function. Its derivative is 1 over the function. I can move this stuff down. All right, so 1 over the function times the derivative of the function. And that always takes an additional step. Right here, the derivative of 3x plus 2 is 3. And then I'm pretty close. Let me put the 5 over 1. Well, I can't because it's in the margin. Thinking of the 5 over 1, that would be 5 over x. And then 1 times 1 times 1 is 3. And the denominator, 2 times 3x plus 2. And that's your answer. Okay? So, you may find this more difficult. A lot of people do. I can't really argue. Just have to, you got your logarithm properties and then your derivative formulas mixed together, and you just got to keep them straight. All right, well, now a couple of places where we would use the derivatives. Number 18 is asking us to determine the intervals where the function is increasing and where it is decreasing. Remember that this involves the first derivative. So for f prime, now this is a sum of 2 functions, so I just get their derivatives separately. So the derivative of x squared, 2x, minus 2, ln of x, I keep the minus 2, and then the derivative of ln of x, that's the simple case. The derivative of ln of x is 1 divided by x. And let's write that. If I think of the 2 over 1, then that's minus 2 divided by x. Okay. All right, so that's my derivative. To get the critical values, I'm going to set the derivative equal to 0. 2x minus 2 divided by x equals 0. All right, so this is an equation with a fraction in it. To solve this, I'll just remind you, to solve an equation with a fraction, you want to multiply both sides by the least common denominator. the least common denominator. In this equation, there's only one denominator, and it's x. So basically, we're going to multiply both sides of this equation by x. Okay. Now, by the distributive property, I'm going to have to take the x times the 2x and the x minus x times 2 over x. And then on the right side, x times 0 is still 0. Notice that right here, those x's cancel. So that's 2x squared minus 2 equals 0. Okay. This is a quadratic equation. I'm going to solve it using the square root method. So divide both sides by 2 gives me x squared equals 1. X will be the plus or minus square root of 1. Whoops. Which would be 1 and negative 1. All right. So I've got my critical values, 1 and negative 1. Now, I mean, you know, just log functions, that's just one of those categories where, you know, things are just not so straightforward, so simple. You got to go back and think the domain of the ln of x is, x has to be positive. The logarithm of 0 is undefined, and the logarithm of negative numbers, that's undefined as well. So even though negative 1 is a critical value, it's not in the domain of our function, so we can't use it. All right. Just lots of things you got to watch out for. Negative 1 is not in the domain of ln of x. And probably I should have started the whole problem by mentioning that. So when we do our sign diagram, remember how we draw a number line that represents the domain of the function. Most of the time it's all real numbers, but with a log function, it's going to be restricted. Okay. So because that original function has ln of x in it, we can only use positive numbers. All right. So although negative 1 was a critical number, can't use it. Therefore, the only critical value that I can use is 1. All right. So yeah. My next step is to break that down into intervals of the domain. And here they are. Little tiny interval from 0 to 1 and then from 1 to infinity, those are the intervals of the domain. It might help if we take a look at the calculus, look at the graph of this thing. Let me get rid of this stuff. So my function was x squared minus 2 times the natural log of x. That's the function that we're speaking of, I think. Got it right. Yeah. Okay. So if I just graph that and just say the standard window, that's what it looks like. All right. So, and let me see if I can just take some space off the left of the graph and the bottom of the graph. Even take some space off the right of the graph, but that's okay. All right, so I'm going to get a picture of this. Actually, before I do that, let's trace over to where x is 1. And you can see that point on the graph. So let's use that. Okay. I'm going back to my document. See if I can. Oh no, please don't do that. Okay. Going to pop that graph in here. So that's fine. That's what I wanted you to see. So there's the graph. And hopefully, you know, that goes along with what I said. It turns out this little piece of the graph, this can, this continues up here forever in that direction. That continues forever like that. So that should hopefully go along with the fact that the domain is 0 to infinity. You should be able to also, it should be pretty clear that the function is going to be decreasing on this first interval. You should be able to see that from the graph. And then it's increasing the rest of the way. The way, of course, we would tell that from using calculus would be get a test number. It has to be, you know, in the domain, and then substitute the test number in the derivative, which was 2x minus 2 divided by x. And then if you put that, go back to the calculator and put the derivative is 2x minus 2 divided by x. And if I go to my table, get rid of all this stuff. All right, I put in 1/2 and 2. That should agree with what I saw, what we saw in our paper. In the first interval, the derivative is negative, and on the second interval, the derivative is positive. That, so negative here, positive here. Oh, geez. It's about to lose it here. So it was negative, positive. Oh. And that's pretty much it. The answer is right here, that my function is decreasing on the interval 0 to 1 and increasing from 1 to infinity. So I guess it'd be nice to write that out. Here's the answer. The function x squared minus 2 ln of x is decreasing on the interval 0 to 1, which also, you know, looks like an ordered pair. That's why I wrote the interval, and increasing on the other one, other interval, which is 1 to infinity. All right. So lots of stuff. Okay. Lots of stuff to do here. Oh, all right. Any question on that one? Oh, all right. Gosh, I thought we'd finish early, but it doesn't look like it. Okay, last problem. An application which says a model to consumers' response to advertising is given by function n, and it says x must be greater than or equal to 1, where n of x is the number of units sold and x is the amount spent on advertising in thousands of dollars. The first question, how many units were sold after spending $5,000 on advertising? Well, X is the amount spent in thousands. So 5,000 would be an X value of 5 because X is in thousands. And so we're just computing n of 5, just putting 5 into the original function, which is just a calculation. Why won't you let me write there? Must be in the margin. Okay. 1,000 plus 200 times the natural log of 5. And that's just a calculation. I'll just do that in my handheld calculator. I get 1321.89. Okay. Actually, that would, how many units were sold? That's not in dollars. And probably round that to the nearest unit. So let's say 1,322 units. Okay. All right, 1,320 units. Part B, find the derivative. Find n prime of x and n prime of 10. So let me remind us, let me put the function down here. It's 1,000 plus 200 natural log of x. So at least this isn't a real difficult one for the derivative. We'll first have our sum rule, the derivative of 1,000 plus 200 times the derivative of ln of x. Well, derivative of 1,000 is 0, and the derivative of ln of x is 1 over x. Thinking of 200 over 1, that derivative is just 200 divided by x. All right. And then n prime of 10, that's just substituting 10 for the derivative, and that gives me 20. All right. Find the maximum and minimum values of n if they exist. So we would do that by setting the derivative equal to 0. Well, my derivative is 200 divided by x. So if I set that equal to 0, I would multiply both sides by x to get rid of the fraction. That gives me 200. And on the right, 0 times x is still 0. Well, 200 equals 0 is just a false statement. And when that happens, that tells me that the equation I was trying to solve has no solution. So what in the heck does that mean? If there's no solution, that means there are no critical values. If there are no critical values, that means there can't be a relative min or relative max, because that's the only place that the relative max or min could occur. All right? Can't happen. So no critical values, no no critical values, no relative max or min. So there are no maximum and minimum values. So let's see what they're trying to get after in this last question. 1000 plus 200 ln of x. So I'm going to look at this in my calculator. 2000. Gosh, I can't even think. It was what, 2000? No, 1000 plus 200 ln of x. All right, so I'm going to just go to my table for a minute. Said n has to be greater than or equal to 1. I'm going to just start looking at numbers, values of x that are getting bigger and bigger. Let's go one more round of zeros. All right, let me copy this. Oh gosh, we're almost out of time, but we're almost done. I'm going to copy this table. So they're asking us to find the limit of the derivative as x approaches infinity. I'm not sure that we want the limit of the derivative, but the limit of the function. So let's go back and remember what X is the amount spent on advertising, and N is the number of units sold. Let's see if it'll let me do this. And that's also in thousands. And the Y1 column is the number of units sold. So we could probably see the same kind of thing. With the derivative and the rate of change, but I think it's pretty clear here that, okay, look, as the number of units, okay, basically, as we continue to spend a lot of money on advertising, the number of units sold doesn't change a whole lot. For example, if you spend $5,000, well, that'd be 5,000, I guess, on advertising, the number of units sold is 2,700 roughly. If you bump that up to 100,000, the number of units sold only increases by about 600. So that's why it says, does it make sense to spend more and more dollars on advertising? No, for what I just said. The number of units sold doesn't increase significantly as more and more dollars are spent on advertising. I would say something like that. As more and more dollars are spent on advertising. Whew. That that is the answer. Sorry, got sidetracked. All right. Whew. So let me stop the recording.